So 1 through 7 is unit 1. 8 through 18 is unit 2. And just FYI, we're going to be going over number 2 on the term review together. Since I've been getting a lot of questions about this one, I think a whole class instruction on it might be a good idea. 19 through 27 is unit 3. And then 28 through 38 is unit 4. And then 40 through 44, unit 5. Less on unit 5 because it was the most current unit and you guys have been doing great practice with the My Math Lab and the practice set already. So just a note on unit 5, and we'll talk about this in the packet as well. You must show your synthetic division and any other solve work. So if the problem does require P over Q, you got to show the P over Q value work, including all those plus or minuses. If it doesn't, you got to show your synthetic division work of depressing the polynomial. So folks, we are going to be starting today in the term review packet with unit 3 stuff, which is on page 2. So for unit 3, you will want to study the parent functions, which are on page 7 and 8 of your unit 3 notes. So parent functions, you'll need to know their key features. And domain and range. Key features being like the parent tables, asymptotes, equations of the asymptotes. So the 12 basic parent functions. And what I want you to notice is that on number 19, on the My Math Lab term review, it does say write the domain of each of these functions. So what I would do is study pages 7 and 8 first, and then try number 19 to see if you really know your stuff with the domain of each of those parent functions. So the other thing in this chapter was transformations. So the big thing with transformations is they are located on pages 10 through 15 of the notes. It's kind of a large span, but we kind of had fragmented sections on the shifts, the reflections, the stretches, and the shrinks. So make sure you understand all those types. My big beware statement with this is the horizontal ones. Those are the ones where we cross our eyes and the sign does the opposite of what we would expect. Or if it's a horizontal stretch or shrink, we reciprocalize the number first and then determine if it's a stretch or shrink number. So folks, we're going to go ahead and just look at this equation above. And what is that minus 1 on the outside doing? So that's going to be a down 1. So outside numbers are always vertical. Inside the function numbers, horizontal. So what's that negative 2 on the inside doing, cross your eyes? It's going right 2 units. So right 2. So opposite of what we would expect for the sign. Now that negative 2 is on the outside. It's being multiplied out in front. What's tricky about that one is it's actually 2 different transformations. The 2 will be a vertical stretch by 2, and the negative out in front will be a vertical reflection. However, you may remember from my math lab that sometimes instead of calling it a vertical reflection, it will say over the blank axis. So if I am vertically reflecting it, top over bottom, what axis are we swiveling over? The x-axis. So this can be a little bit confusing because we think vertical, we think up and down, we think the y-axis. But how we are actually reflecting, or what we are actually reflecting over, is over the x-axis. So I would be careful with this terminology because a horizontal reflection would be over the y-axis. And I remember that being an issue on these types of problems on the Unit 3 test. For the parent function, know the names or the equations. I want you to change that to and. What type of function is this? It's quadratic. It's got that happy little power of 2. So this is a quadratic. And the parent equation looks like y equals x squared. I don't think I'd really mess around with these graphing practice problems. I mean, you can if you want. Just make sure if you're doing the h of x one, you use a calculator since it involves base e, which we never memorized the parent table for. But I would mainly focus for this unit on the MyMathLab term review questions. Down at the bottom, we see our other concept from Unit 3 besides the parent functions and transformations, and that's piecewise functions. You'll find things about the piecewise functions on page 9. But one of the big things is points of discontinuity. Let's hear. Points of discontinuity occur at bound lines when I have an open dot going this way and a closed dot going that way. Discontinuous means I can't draw it without lifting my pencil. So continuous means I can draw it in one fell swoop. Discontinuous means I would have to jump to get up to that other section. Sometimes piecewise functions are continuous. They're continuous if the open dot and the closed dot occupy the same space. Because if they have the same value, is there actually a break there? No. Since it is undefined for this function piece, but this function piece covers it, so undefined here, this function piece covers it, that would be continuous. So they occur at the bound lines or bound values. So in order to determine if you do have a point of discontinuity, you might want to do a little sketch or maybe just look at the tables. So your bound lines come from your bound statements. And the bound values are all of the numbers involved in those bound statements. So we're going to go ahead and see if we can evaluate all of these inputs in that piecewise function. So if I want to find h of 0, we want to see where 0 puts us as far as the bound statements go. Is 0 less than -4? Nope. Is 0 between -4 and 2? Yes. So that means for this one, we would use this function piece. Hey, wait, there's no place to plug in an x value of 0. So what is h of 0 equal to? 1, that constant value. For the next one, h of -10. -10 is less than -4. So we will use that part of the piecewise function. A half of negative 10 is negative 5. Negative 5 plus 6 is 1. What's the absolute value of 1? 1. So that's what h of negative 10 is equal to. Now, looking at the next one, if you're like, I don't see square root of 4 anywhere in those bound statements, what is the square root of 4? Just 2. So remember, we don't include a plus or minus here because I'm just including the principal root. So this is really asking what h of 2 is. So, am I going to plug 2 into the second function piece or the third function piece? The third, because 2 is not less than 2, but it is greater than or equal to 2. So we're going to plug into this function piece. So 2 squared is 4, and 4 minus 5 is negative 1. Try the last one on your own. Negative 4 is greater than or equal to negative 4, so we use the second function piece, and it is equal to 1. Folks, that's it for Unit 3. Anybody have any questions? All right, then. We are going to move to the first page. Actually, go ahead and flip to the back page for a moment. I just wouldn't even bother with this number 14 on the back. So if you're looking for extra practice, just go ahead and skip 14. So flipping to the front, we are now ready to talk Unit 4. Unit 4 was one of the heftier units, but the big overall arching theme kind of centered around graph key features and restrictions. So we're going to break down the 3 types of problems that are on this page. We've got the top 2 problems, A and B, which is finding the inverse. Of 2 functions. Inverses are going to be on pages 10 through 11. And on the test, you will need to show your inverse solve work, which you can see on the MyMathLab term review. We got to show the work for finding the inverse equation on 37 and 38. And then state the domain and range for both the function and its inverse. Folks, I would put stars by these 2. Because this was probably the more frequently missed question on the Unit 4 test. Actually, I think it was the most frequently missed question. So we're going to spend some time with the inverses. And what's hard about inverses is if I have a function with a, actually let's do that blue. If I have an original function, f of x, with a domain and a range, how do I actually find the inverse? What's the big crux of what an inverse is? Y and x switch. So when you see inverse, you think switch x and y. But it's not just x and y in the equation, it's x and y as a whole for the domain and range of the function. So if I find the inverse equation, it's going to inherit all the restrictions from the domain and range, but they flip. So the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. So a lot of people found the original domain and range and just stated the domain of the function, but everything x and y value-wise switches from the function to the inverse. So I would put a big important box around this. Our next big concept for C and D are function operations. Which are going to be on page 7. And again, folks, this is to model what studying for finals looks like on the college level. I'm giving you the page numbers because you are learning, but what you would want to do is look back in your notes and say, hey, there's inverse as a heading. What do those inverse problems look like? So I'm just doing a little bit of the work for you so you can see, hey, this was helpful because I knew exactly where to go to find those types of problems. So in college, maybe you want to use Post-it notes in your textbook or like label, hey, this all covers like one specific type of problem. It is a great way to study and then easily find things for your final exam. So the big thing with function operations is we need to consider all the restrictions when we are thinking about the domain. That means functions on, or restrictions on F, restrictions on G, and the resultant restrictions. And they use h of x in some of these problems, so h of x, whatever. All the functions involved, we have to consider the restrictions for. And then the problems down at the bottom are the composites. Bless you. Bless you. Composites, which you will find on page 6. Now, the first thing that bears mentioning with composites is notation. To the right, you see the parenthetical notation, f of g of x, and then h of g of x. We also have the Fogg and Goff notation, which we also read as f of g of x and g of f of x. And just make sure you don't get that open dot confused with any multiplication function operations. The open dot indicates composite. Now, when we consider the restrictions for a composite, we have to consider the inner function restrictions and the final composite restrictions. So being able to identify the inner function is important. Who's our inner function on problem E? G. Who's our inner function on F? G again. Over here, F is my inner function, so again, not as intuitive over here. And G is my inner function. And the inner function is whichever one you are plugging in for the input of the other function. So being able to keep these restrictions and how we calculate them straight is a very large part of Unit 4. Remember, this was the section where partial credit was very minimal because if you do a bracket versus a parenthesis, you missed a restriction. If you have a different value or included a negative infinity on one end, you have included an extra restriction or excluded one. So this is a very fussy part of the term test, so we're going to spend some time on this page. So any questions on any of those guidelines so far? So let's talk restrictions. Restrictions. In Unit 4, there were 2 types of things that gave us restrictions. The first is a square root. Square roots with the radicand under the square roots yield a restriction because the radicand has to be greater than or equal to 0. Why? If we're talking about domain restrictions, why does our radicand have to be greater than 0, greater than or equal to 0? What don't we want in our domain? negatives under the square root, which cause imaginary stuff, which is not graphable. So there's our first type of restriction, square roots. Our second type is when we divide by 0. What happens when we divide by 0? Undefined, also not graphable. So anytime I have dividing by 0 or the possibility of dividing by 0, we are going to have the fact that x can't be equal to some number. So fractions can cause restrictions, square roots can cause restrictions. So keeping this in mind, we're going to look at those 3 functions up at the top, which are what we are going to use on this entire page, and we're going to see what restrictions these functions have. So I've got a quadratic. No restrictions. Nope, we're not going to write the domain. Domain would be all real numbers. Going to write no restrictions. Happiness. How about that square root? Restrictions? Yeah. So we're going to take the radicand, which is 2x minus 7. We're going to say, hey, that needs to be greater than or equal to 0 to keep my stuff positive. So 2x greater than or equal to 7. So we divide by 2. So x is greater than or equal to 7/2. So restriction. Now for the last one. Is this function going to have restrictions? Yeah, we've got division, which means there might be some variable we can put in that's going to make that denominator easy. The easiest way to tell what those values are? Factor difference of squares, x plus 3, x minus 3. So we have 2 restrictions. X can't be equal to negative 3, and x can't be equal to 3. Because both of those values would make it dividing by 0. Questions? All right, let's get after it with the inverses then. So first it says find the inverse of g of x. We're just going to start with g of x and figure out its domain and range. Right. How are we supposed to do that? Keeping in mind that this is a non-calculator part of the test. I'm not going to restrict your calculator use, but we should be able to do this without a calculator. So, do I know about my domain? Yeah. We know that the x values for this greater than or equal to 7/2. How do I say that in interval notation? Bracket 7/2. That's where it starts, included value, and it goes to infinity. And if you're like, all right, sure, fine. Question?
Can we do it in decimal format, or do you want it to be in fraction?
I'm not sure if my math lab will accept decimals. We'd have to check on there, but I would say steer more towards the fractions. But if it doesn't specify, you should be able to do both. I would give you full points for that. For the range, let's talk transformations for a second. Are there any vertical or up-down transformations for this function? Nothing on the outside of that square root. So if my parent function has a vertex at 0, 0, we move it to the right 7/2 units, but where is the y value of the vertex? It's still 0. So this is going to be bracket 0 to infinity, but you could check yourself on your calculator as well. So this is important. I have to find my original function stuff first so that I can use that to find the inverse, domain range. So let's find the inverse of g of x. So first, the notation. The inverse of g of x means this. It's written as g to the negative 1 of x, but it's read as the inverse of g of x. So that's the inverse. So let's go ahead and show our work for finding our inverse over here. We start with function g. G of x equals square root of 2x minus 7. What should I do first?
Flip the sides.
We want to switch x and y, but currently it's like, well, there isn't a y. Well, g of x is the same as y, so let's go ahead and replace that. And now we can switch x and y. Everything else stays locked in. So x equals square root of 2y minus 7. Folks, at this point we are looking at the inverse, but do we want to leave it as an x equals equation? No, we want to write it as a y equals equation because that would be something that we could graph. So how am I going to break that y out of that square root? Square, square both sides. Not quite as fun to say square root, but that's what we need to do to get rid of that square root. So then x squared equals 2y minus 7. We're going to add the 7 to move it over to the other side. Sidebar up here. And then we're going to divide by 2. So x squared plus 7 over 2 equals y. It seems fussy, but why is this not our exact final answer? We don't have to split them into 2. You could, and that would be fine. There's something about the notation. We have to say this isn't just any quadratic. It's specifically the inverse of this. And that's why it's going to inherit the original function's restrictions. So it seems fussy, but I have to replace that y with the inverse notation. Because that's what says this isn't a regular quadratic. Because what would a regular quadratic's domain be? All real numbers. But what is the domain of this quadratic going to be? The range of the original function. So this notation is important because it says this isn't just a quadratic, it's the inverse of this one. So that means the range will be bracket 7/2 infinity, and the domain will be bracket 0 to infinity. Folks, what questions do we have on that inverse problem? Study this one. It's a good one to study. Domain and range, why they flip, why we should say them first. Get some good practice with that on my math lab. For B, you don't have to find the domain and range for this one. I just want you to see if you can find the inverse equation. Go. For h of x. Hopefully you were able to get to here with switching the x and y. But if you got to this point and were like, how am I going to isolate that y? The big problem here is where the y is located. It's in the denominator. We need it at ground level in order to be able to isolate it. So from here, we are going to multiply both sides through by the denominator, which gets it out of the denominator on that side and moves it to this side. Let me go ahead and draw a line here. So from here, it's tempting to distribute that x. But if I distribute that x in, that's just going to give me xy squared, and I'm making that y term more complicated. So it's actually a better move to just divide by x. So then y squared minus 9 equals 1 over x. We add 9. Y squared equals 1 over x plus 9. What now? Square root, square root. And when I square root, what do we need? Plus or minus. So that's a big one because we're square rooting as an operation. And the final step is replacing that y with that inverse notation. So h to the negative 1 of x equals plus or minus 1 over x plus 9. So yep, that stuff under the square root is super gross, and it just stays super gross. And that's what the inverse equation would be. Folks, we're going to go ahead and take a quick breather before we move on to the next problems.